In section 2.3, we're going to solve radical equations both graphically and algebraically. So say we're asked to solve the following equation. 7 is equal to the square root of 12 minus x plus 4. When you're solving radical equations, the first thing you want to do is you want to isolate the radical sign, meaning get it by itself. So I'm going to subtract 4 over to the other side. So I'm going to get 3 is equal to the square root of 12 minus x. And then I'm going to square both sides to get rid of the radical. So squaring the left side, 3 squared is going to be 9. Squaring the radical, when you square a radical sign, the radical sign disappears and you're left with whatever under the radical sign. And now I'm going to isolate x. So I'm going to add the x over to the other side. And I'm going to subtract the 9 over to the right side, and I get an answer of x equals 3. Now, once you solve for x, you want to verify. And when you verify, you want to plug it back into the original equation. So does 7 equal the square root of 12 minus 3 plus 4? 12 minus 3 is 9. The square root of 9 is 3. And 3 plus 4 is 7. So yes, this is a valid solution. All right, we also might be asked to solve this graphically, and there's a number of ways you can solve it graphically, but the easiest way to solve this one graphically might be to, again, isolate your radical. So I'm going to get 3 is equal to the square root of 12 minus x. And now you're going to go graph y equals 3 as one equation and the square root of 12x as another equation. Okay, so graphing y equals 3 is pretty straightforward. It's just going to be a horizontal line at 3. Okay, now to graph the square root of 12 minus x, you may want to factor a negative out under the root sign, which is going to change it to be x minus 12. So now using our transformations, we know that b is negative 1. And we know that h is equal to 12. So basically, b being negative 1 means there's a reflection in the y-axis, and h being 12 means that it's shifted 12 units to the right. So that means I'm going to be here, and I'm going to be moving to the left. Okay. Well, we could also make a table of values for this if it makes life easier for ourselves. Okay. So we know that, and we could plug the table of values in here or here. If x is 12, y is going to be 0, because 12 minus 12 is 0. If I put a 3 in for x, 12 minus 3 is 9, and the square root of 9 is 3. And let's try one more. Let's put an 8 in for x. If I put an 8 in for x, 12 minus 8 is 4, and the square root is 2. So I have the point 12, 0, 3, 3, and 8 and 2. And if I graph this second function, which is a radical, it's going to look something like this. And the two graphs intersect at the point where x is 3. So therefore, the solution is going to be x equals 3. So that is how we solve graphically. Now, graphically can be a little bit more challenging if the equations are a little bit more confusing. But again, if we use our transformation skills, it shouldn't be too bad. All right, let's determine the roots algebraically for this one, and then we'll look at them graphically. So again, in part A, to determine it algebraically, I am going to isolate the radical. So here is my equation to start with. To isolate the radical, I'm going to move the 3 over to the other side. And then I am going to divide both sides by 2. So I'm left with the square root of x minus 4 is 3 over 2. And now we're going to square both sides to get rid of the radical. So x minus 4 is going to be 9 over 4. Remember, when you square a fraction, you square the top and the bottom. And I'll just take it up here. So now I'm going to have 9 over 4. I have to add 4 to the right-hand side. Adding 4, if I put that in quarters, is really 16 over 4. So x is going to be 25 over 4. again, if I was to verify this, I would take my equation or my answer and plug it into my original equation. So it's going to be 2 the square root of 25 over 4, subtract 4 minus 3. Does that all equal 0? Well, again, you would have to get a common denominator under the root sign. So 4 is really 16 over 4. So this is going to be the square root of 9 over 4. Well, the square root of 9 over 4, you square root the top, you square root the bottom is 3 over 2. These 2's will cancel, and 3 minus 3 is 0. So yes, 25 over 4 is a valid solution. Again, to draw this, do this one graphically. Okay, let's just try this a different way than the first one. We already have the equation set up equal to 0. So I have 2, the square root of x minus 4 minus 3 equals 0. And we know our base function is the root of x. So the root of x, and the basic points are 0, 0, 1, 1, 4, 2, 9, and 3. And looking at our transformations, I know that a is 2, h is 4, and k is negative 3. So again, using my mapping notation, x over b plus h is going to be x plus 4, and ay plus k is 2y minus 3. And again, we are going to do our mapping notation. So I'm going to take these x coordinates, plug them in there, and they'll end up as my x coordinates of my new graph. So 0 plus 4 is going to be 4, 1 and 4 is 5, 4 and 4 is 8, 9 and 4 is 13. Then I'm going to take my y coordinates, plug them in here, and they're going to become the y coordinates of my new graph. So 0 times 2 minus 3 is minus 3, 1 times 2 minus 3 is minus 1, 2 times 2 minus 3 is 1, and 3 times 2 minus 3 is 3. So therefore, my graph is going to be 4 and negative 3. So when it's 4, it's negative 3. 5 and negative 1. Whoops, wrong way. 8 and positive 1. And the last one was 13 and positive 3. Again, if you graph this, whoops, my graph looks like that. And the solution is going to be wherever the graph crosses the x-axis, because now the equation was equal to 0 and y equals 0 at the x-intercept. And again, because it's halfway in between 6 and 7, it's hard to tell algebraically, but we know, because it's hard to tell reading it off the graph, but we know from algebraic solution that the answer is 25 over 4. So that would be our final answer. So again, you could graph like we did in the first case where we graphed both sides individually and found the intersection point, or you can set the equation to 0 and just graph it and find the x-intercept. Okay, let's take a look at the next example. And again, this time we want to find the roots of the square root of x plus 5 minus 3. So again, I think we'll do this with your turn. So pause the video and give this one a try. Okay, hopefully you've had a chance to try this. So for part A, again, we are going to isolate the root sign. So I'm going to add the 3 to the other side. And then we're going to square both sides. Subtract 5 from both sides, and x is equal to 4. Now I want to verify this in the original. So 4 plus 5 minus 3, does that equal 0? Well, then this under here is 9. The square root of 9 is 3. So yes, 0 equals 0. This is a valid solution. Now, to do this one graphically, sorry, we have a couple of options. Okay, we could just leave it the way it is. And if we do it the way it is, I know that this is basically my root graph. And we could almost do this one by inspection, because this means it's shifted 5 units to the right and up or down 3 units. So on my graph, I know these are my base points for the root of x. And if I do it just by observation, I'm going 5 left and 3 down. So 5 left and 3 down puts me right there. 5 left and 3 down puts me right there. 5 left and 3 down puts me right there. And 5 left and 3 down puts me right there at 4. And if I graph this, my graph crosses the x-axis at x equals 4. So again, my solution is the x-intercept of x equals 4. All right, a couple more and we are done. Now we're just going to deal with these algebraically. We want to solve this one. So again, this one is a little bit more challenging, and you'll see why shortly. So again, the first goal is to isolate the radical. So this is going to be square root of x minus 1, and I'm going to subtract 3 to the other side. Now I need to square both sides, and this is where people make a mistake. Squaring the left side is simply x minus 1, because again, when you square a radical, you're left with what's underneath the radical. When you square x minus 3, this really means x minus 3 times x minus 3. So you have to multiply this out to get x squared minus 3x minus 3x plus 9. So I end up with x squared minus 6x plus 9. Now we are solving a quadratic equation. How do I know it's a quadratic? Because I have an x squared there. And to solve a quadratic equation, we learned in Math 20, Pre-Calc 20, that you must set your equation equal to 0. So that means I'm going to subtract my x over to the other side to get minus 7x. I'm going to add 1 to get 10. So there's my quadratic equation. And now, using our factoring skills, this is going to factor into x minus 5, x minus 2. So therefore, either x minus 5 equals 0 or x minus 2 equals 0. So my two solutions are x is 5 and x is 2. So now we want to verify. And again, we always verify back in the original. And the original was 3 plus the square root of x minus 1 equals x. So let's start with 5. 3 plus the square root of 5 minus 1. Does that equal 5? Well, this is 3 plus the square root of 4 is 2. Yes, 5 equals 5. This is a valid solution. Let's try the other one now. Okay, and the other one, if I stick a 2 in there, I get 3 plus the square root of 2 minus 1. Does that equal 2? Well, this is 3 plus the square root of 1 is 2. 4 does not equal 2, so this is not a valid solution. So my only valid solution is x equals 5. Again, if we look back at the original question, some of you might be wondering, why is that restriction in there that the domain has to be greater than or equal to plus 1? Well, remember, when we deal with radicals, you can only square root positive numbers. So the term under the radical sign was x minus 1. So that would have to be greater than or equal to 0. So therefore, if you isolate the 1 to the other side, my domain is x is greater than 1. And that's why they have that as the restriction for the domain. Okay, the last one is we're finding approximate solutions to radical equations, okay? We're not going to worry about this one graphically. We're just going to do it algebraically, because when we're trying to approximate solutions graphically, we're just guessing, and it's not a very valid way to do them. So let's do this one algebraically. So the first thing we're going to do is we are going to subtract the 4 over to the other side to get x minus 8. And then again, we're going to square both sides. Squaring the radical is going to be x plus 4. Squaring the binomial, again, you can write it out twice and FOIL it, or you could do the shortcut. for squaring a binomial. And remember, the shortcut is you square the first term to get x squared. You multiply these together and times by 2 to get negative 16x, and then square the last term to get 64. So again, we're solving a quadratic equation. So I want to set it equal to 0. I have x squared minus 17x plus 60 is equal to 0. And now there are no two numbers that multiply to give me 60 that add to give me negative 17. Oh, hang on. Yes, there are. Sorry. We can factor this into x minus 5 and x minus 12. Okay. And therefore, either x minus 5 equals 0 or x minus 12 equals 0. So either x is 5 or x is 12 would be my two solutions. Again, we want to verify that these are accurate. So we're going to go back to our original equation, which is 4 plus the square root of x plus 4. Does that equal x minus 4? We will substitute in 5. So 4 plus the square root of 5 plus 4. Does that equal 5 minus 4? Well, this ends up being 4. The square root of 9 is 3. This does not equal, so this is not a valid solution. Now we'll try 12. So 4 plus the square root of 12 plus 4. Does that equal 12 minus 4? So this is the square root of 16. 4 plus 4, the square root of 16 is 4, so I get 8 equals 8. So yes, 12 is a valid solution. All right. Well, that pretty much ends our section on solving radical equations. So there's your assignment. If you have any questions, feel free to ask. When it says use a calculator for number 3, you might want to use Desmos to solve that. That might be the easiest way to solve that graphically. All right, good luck.